Hello, pre-algebra. Hello, 7th graders. We are into the last section of chapter 10, similar solids. So we're going to use something we learned with similar polygons a while back. And similar solids. If solids are similar, something is the same, but not everything is necessarily the same. I don't think that was grammatically correct, but there must be something the same. And so when we think back to our polygons, if we had two triangles that were similar, we might have one that looks like this and one that looks like this, right? So what is the same is the shape. The size could be different. So similar solids have the same shape, different sizes. We will find that the corresponding edges have equal ratios. And that helps us find a scale factor, just as we did with the two-dimensional figures. So let's try this. If I have an original figure, let me do it this way, an original figure that I'm calling the parent figure, go ahead and pause the video and draw that figure, and also draw figure A. We're going to compare these two figures and see if they're similar. Just a moment. Okay, so the first thing we want to do is identify corresponding edges, right? So, and then we need to set up ratios to see if these are similar. All right, so it looks like these two figures are facing kind of the same direction in space, right? They're orientated the same way. So we have a triangular base, two triangular bases. These are what kinds of figures? Two bases, so solids, right? I'm sorry, so prisms. And we have the triangular base of the figure A in the same position as the parent figure, okay? So if we could compare, we could set up ratios that go from that compare the, let's say the new figure to the parent. See what happens when we do that. So the new figure, if we look at side 6, what side is corresponding to side 6 in the parent figure? So the parent figure has side 3. Okay, good. Let's see if that ratio is the same as the other leg in our base. So the new figure has this leg of 10, right? And which corresponding edge can be found in the parent? And hopefully you are saying 5, right? And so the question is, are these ratios equal? And your answer is yes. They both equal what value? Good, 2. And so let's see, we could even prove that these two figures are similar by checking out the last dimension that we were given. In the new figure we have 18, which is the height of the prism, distance between the bases, right? And in the parent figure we have 9. And you can see that that ratio also equals 2. So the scale factor for this pair of similar prisms is 2. All right? Good. Let's see about figure B. And again, you might want to pause the video and draw the figure and come back. Okay, in this figure, this particular figure also looks like what type of figure? Good, a triangular prism, right? However, it looks like it is in a different orientation. It's been kind of turned around or swiveled or turned upside down or something like that, right? So we have to be careful finding the corresponding edges of this figure. Let's use the same setup for our ratio. We'll take the new figure and compare it to, put it over the dimension of the old figure. So probably the easiest dimension to look at is the height between the two triangular bases, right? In the new figure it's 27, but in our parent figure it's 9, right? Okay, let's see if we can find another pair of corresponding edges. So let's go with the new figure. How about this bottom dimension of 6? So see if you can complete the corresponding edge in the parent figure. And hopefully you see it is 3. It's the shorter of the two legs of that triangle, isn't it? And then finally, The final side of that triangle is 9, right here, and it would correspond with the longer of the two sides in the parent, 5. So let's put little question marks over these ratios because we're testing to see if figure B is similar to the parent. So if we simplify these ratios, what is 27 over 9? We could call that 3 over 1, right? And how about 6 over 3? That simplifies and becomes 2 over 1. Are those two ratios equal? No. So we can strike that out. So can we say that these two figures are similar? No, not similar. We don't even have to look at that third ratio, do we? Although we could look at it and we see that it equals 1 4/5, 1.8, and neither of these ratios equal 1.8. So these figure B is not similar to the parent. So we're going to make a rule box for similar solids ratios. And we're going to kind of leave it behind for a minute, leave about 3 lines, and we're going to go check something out and come back and fill in the rule. We can add 1 line before we leave, and that line is for similar solids with scale factor K. Okay, we'll leave it at that and we'll come back. Okay, so recall that, and you do not need to draw this at this point, just fold your hands on your desk and listen. Recall that surface area is kind of interesting. If we say in this figure that the side has a length of 4, and I tell you in this figure we have a side that has a length of 8, and let's say this is a cube, so the dimensions are going to be the same in the horizontal and vertical dimensions, right? If we just look at the front face of these two figures and we find the area, right? Look at what happens. To find the area of figure A, the area would equal what? Base times height, right? So in this case, it's 4 times 4, right? And 4 times 4 is 16, okay? So when we move to figure 2, how has the scale changed? Going from 4 to 8. What is the scale factor there? K would equal, what do we multiply by to get from 4 to 8? 2, right? So when the scale factor equals 2, can we just multiply the area we just found by 2? So if we could, is the area of this new figure here 16 times 2 or 32? Is that what this is? Let's go see by experimenting with the values given. So the area in this new figure is given by base times height as well, isn't it? And so let's plug in the known values, 8 times 8. And 8 times 8 is 64. It is not 32. Isn't that interesting? So the scale factor of 2 is related to the factor we need going from 16 to the area of 64, but we can't just multiply by 2, can we? We are going to have to multiply by 2 times 2. Remember, this dimension here is multiplied by 2, and this dimension here would need to be multiplied by 2 in order to get over to the new, bigger figure. So that if we're going to use a scale factor with area, we're going to have to square the scale factor, right? And what do you think will happen when we're talking about volume? If we increase a cube on every side, length, width, and height, right, by 2, it will increase the scale factor for volume by 2 to the, what will the exponent be? Good, to the 3rd. So recall, this is what we covered in chapter 8, and here we are using it here, okay? So let's put this in. Surface areas have a ratio of the scale factor squared, and volumes have a ratio of the scale factor cubed. All right, so let's go ahead and use what we've just been talking about in a real example. Pause the video and take this down. So we're looking for the larger solid's surface area and volume. Let's start with surface area. All right. We know that we have a scale factor of 1 to 3. So when we look at that, we know that the smaller solid would be on top, right? Small on top compared to the larger number or the larger solid on the bottom. That's just a little note, okay? That's what we're working with here. Okay, so we have that factor of 1 to 3, but right now we're talking about surface area, right? Surface area. And we know that area, we must take that ratio, and because we're talking area, we don't just leave it by itself, but we square it, because area is squared, right? And so let's take a look. Which do we know, the smaller or larger surface area? We know the smaller one, so we have to put that across from the top, right? Where we have the smaller piece of the ratio, 135 centimeters squared, and we don't know the larger one, so we leave that unknown. X is the larger solid's surface area, okay? What is 1/3 squared? 1/3 times 1/3, we practiced this yesterday, right? And that is 1 over 9, right? Good. Equals 135 centimeters squared over X. Now we'd simply solve a proportion. You could use your, what? Cross product property, right? You could even use your blowing up a fraction. If we use cross product, we bring 1 times X up equals 9 times 135 centimeters squared. All right? And with your assignment today, you may use your calculator. So X equals 1,215 centimeters squared. Good. So this is a larger value than the small figure, right? And that makes sense. It should be larger. Good. Let's talk about volume now. All right? Okay, we're finding the volume of the larger solid. Okay? We still have our scale, but now we're talking volume. So what will we do to our scale factor? We will cube it for volume, right? And that equals the smaller figure, volume, over the unknown larger figure volume. Very good. So now we're going to cube 1/3, which is 1/3 times 1/3 times 1/3. And 3 times 3 times 3 is 1 over 27. Equals 110 centimeters cubed over, let's use our cross products, right? And we have X equals 27 times 110 centimeters cubed, okay? So X equals 2,970 centimeters cubed, all right? So the volume of a larger 3D is a lot bigger than the volume of the smaller, which makes sense, knowing that we had to cube the scale factor, right? Good job. This is a short assignment, and you need to be very meticulous and detailed with your work. Make sure you check your work carefully. Do a good job. Have fun.